This is tutorial 12. It is about sesqui linear form and spectral theorem. Before solving, let us state some theorem and some definitions. So, what is sesqui linear form? It means it is a form, that is, form means it is a map from V cross V given inner product space, finite dimensional inner product space V, and it is a map from V cross V to the given field K, or maybe F. V is the vector space over the field F. Then we may define F V comma W, and it need to satisfy some property, that is, if we write this combination A1 V1 plus A2 V2, and if we fix the second coordinate, this is same as A1 FV1 plus A2 FV2. Sorry, this comma W, it is F of A1 times FV1 comma W plus A2 times FV2 comma W. So it behaves like inner product. And similarly, if we take a combination in the second coordinate, then suppose we take the combination A1 W1 plus A2 W2, this combination, then again it is same as A1 times, now we need to take conjugation, so A1 bar, that's why it is called sesqui linear. So it is not completely bilinear, so it is linear on the first component and conjugate linear on the second component. So it is A1 times F V comma W1 plus A2 bar times F V comma W. Okay. So this is called sesqui linear form, or in short, it will be called a form. And some properties are like this. So suppose alpha 1 up to alpha n is a basis. This is a basis for V, the vector space V. Then this is the basis. Then this f of x1 alpha 1 up to if we take the combination sum xi alpha I, and second combination it is yi alpha I. So I am writing x as sum of xi alpha I, and second vector y as sum of yi or yj alpha j, whatever you choose. J, I and j both varies from 1 to n. So this can be written as, by those two property, that is linearity and another is conjugate linearity. So by those two property we can write this as xi yj bar times f of alpha I alpha j, alpha I comma alpha j, where ij both varies from 1 to n. Okay. Therefore, any such kind of form, it can be written as it has a matrix representation. So we can it can be written as y star a x, where the ijth component of this matrix, it is simply that f of alpha not al, so it should be AJI. So if we write AIJ, this will be f of alpha j alpha. Okay. So this AIJ, this A matrix, it is called matrix of the form of the given form F with respect to the basis B. Okay. So this is the formula. You can easily check it for 2 by 2 matrix, and you can simply write the explicit formula for any n by n. And there are some, so if we change the basis, for example, suppose B is the first basis, now we are changing the basis, suppose B dash be another basis, which is alpha 1 dash up to alpha n dash. Okay, so there will be a change of basis matrix, right? Another basis. Therefore, we can write alpha 1 dash this as Pij sum of alpha I, where j varies from this is alpha I. So sorry, this will be alpha j dash. So I will varies from 1 to n. Then this P is called change of basis matrix, right? Change of basis matrix. Then we can easily see that the new matrix. So if A dash is the matrix of the same given form, that is of the form F with respect to new basis B dash, then this this A dash, it can be written as B star F. Okay. So those are some important formulas which need to be remembered. And some definition are like this. So something is called Hermitian form. Hermitian form. If f of alpha beta again 2 vector from V, alpha beta 2 vector from V. V is the inner product space, given inner product space. If this is same as f of beta alpha conjugate. Okay, this is for all alpha beta belongs to phi, and this is equivalent to, so this is actually equivalent to another thing I should write, that is okay. Another interesting fact, any form, so given any form F, we can associate it with some linear transformation. Okay, so any form can be written as, so f of for any given form f of alpha beta, this can be written as T alpha comma beta for all alpha beta. Therefore, we are this result says a form arises from a linear transformation. So there is a one-to-one correspondence, and moreover, this correspondence is actually it is linear isomorphism. Okay, so this is an important result. So it is similar to that linear functional, right? Any linear functional can be written as some inner product. Any linear functional will arise from some inner product. Similarly, any form, it will arise from some linear transformation. So any form can be written as inner product with respect to some linear transformation. Okay. So those are some important consequences.
Sir, how can we relate bilinear form with this linear transformation, sir?
Yes, that is that actually that can be proved using that Riz representation, right? That actually directly obtained from those representation lemma. That is any linear functional. You know that given any linear functional f from v to k, it can be written as phi v can be written as some v comma w. It arises from some inner product.
Yes, sir.
That is, there exists some w such that all phi v can be written as v inner product of v comma w.
Yes, sir. Uniquely.
Maybe this is called Riz representation lemma.
Yes, sir.
So from here you can prove this fact. This is not difficult to show, and it is actually already proved in the book, so you can look at it. Okay. So, uh, so this is Hermitian form, and interesting fact is that we know that this form actually corresponds to some linear transformation T, right? So this f alpha beta equal to f beta alpha for all alpha beta. This is equivalent to saying T equal to T star. It is also very easy to check, right? This, let us check this. That is very easy. So I am checking. So f of alpha beta is same as T alpha beta. I have earlier said this is true. So this is T alpha beta, and right hand side is f beta alpha, which is T beta comma alpha and their conjugation. But this side T beta alpha. So if this side can be, left side can be written as alpha comma T star beta, and right side can be written as, so that result is actually true for finite dimensional. Again, finite dimensional linear product space. Otherwise it may not be true. So alpha comma t, because we are using this representation, okay? So t beta comma alpha, this also can be written as alpha comma t beta by symmetry, right? Conjugate symmetry. If we exchange two coordinate, we need to put a conjugation. Conjugate symmetry of inner product. Right hand side we are using. Now alpha comma t star beta. Just compare those two things. From comparing, we are getting t star equal to t. So Hermitian form, if and only if T is Hermitian, right? Or T is self-adjoint, whatever we say. For matrix, we call it Hermitian matrix. T is self-adjoint. Okay, those are some interesting properties. And another thing I should say that another important thing you can look at in the book, that is very easy to prove again. F of alpha alpha for a form F, for a form F, if f of alpha comma alpha, this is greater equal to 0 for all alpha, then this will imply f is Hermitian, and the converse is also so true. If f is Hermitian, converse is easy to see because you can put alpha here. F of alpha alpha, this is same as f of alpha alpha conjugate. So something is same as conjugation of that thing. That means this must be real. So f is Hermitian, this will imply, sorry, I am writing something wrong. This is real. If this is real for all alpha, then the reverse is also true. That is, this side is easy to see, and for this side, a small proof is needed. So from here, it is clear that therefore we are getting a corollary, that is T is self-adjoint if and only if T alpha comma alpha, this inner product is real for all alpha. This is real for all alpha. Okay, alpha belongs to the vector space V. So those are some important properties. Another thing I should mention. So this is also clear, right? Because for every Hermitian form, from here we are getting some self-adjoint operator, and conversely for self-adjoint operator, what we are getting T alpha comma B beta. This will be also Hermitian form, right? So self-adjoint operator correspond to some Hermitian. There is one-to-one correspondence. Therefore, this is also T alpha alpha. This inner product is real. That is equivalent to, because f of alpha beta, this can be written as T alpha comma beta. So this is real is equivalent to saying that T alpha comma beta, this is T alpha comma, this f alpha comma alpha is real. This is equivalent to saying T alpha comma alpha is real. So those are some important facts. Another thing is called principal axis theorem. Axis theorem. This theorem says, given Hermitian form, so F is a given Hermitian form, then it has a diagonal matrix representation. So suppose if F is Hermitian, then F has a diagonal matrix representation with respect to some basis. So diagonal means diagonal, and all those diagonal entries are real. Okay, so diagonal real matrix. So this is actually, that is also known because for any self-adjoint matrix, any self-adjoint matrix can be diagonalizable. So that proof of this thing can be proved using this factor. PAP inverse is diagonal, and all those diagonal entries are real because eigenvalues of self-adjoint matrix, actually those eigenvalues are real. So those are some properties. So let us solve the first problem. Okay, it is not related to that sesqui linear form, but here the problem is every self-adjoint linear operator T defined on an inner product space V has an eigenvector. Is it true? It says that.
Yes, sir.
So yes and no, both. Because why this is true? This will be true for finite dimensional vector space. So
Yes,
this
sir.
is
Finite, this is true always.
is not true.
For finite dimensional, it is true, no, always.
Yes, it will be true. It will be true if V is finite dimensional. Okay. Otherwise, it is not true. So let us construct an example for which this is not true. So
So right shift operator.
yes, I have already given that example. Right shift operator has no eigenvalue.
Sir.
Yes. So let me write this. So if we take the inner product f comma g, so consider this space vector space V. Counter example. So consider the vector space V, which is V consists all polynomial or all what is this called, all continuous function. Okay, all continuous function from R to R, suppose R2 close 0 1. Okay, so now if you see, or maybe R2R, there is no issue. So if we define the inner product Fg defined by that formula Fg bar dt. Okay, F and G are function of t from 0 to 1, and consider the linear transformation, linear operator. This is defined by t of f. This is same as x times f, maybe t times f, because t times f, f applied on t. Okay, so if we consider this linear operator, then we can see that t has no eigenvalue, but t is actually symmetric. You can see that t is actually symmetric operator, self-adjoint, because what is t star? T star is actually t. Tf comma g. This is same as integration tf g dt. 0 to 1. This is same as 0 to 1 f times tg dt, but this is same as f times tg. So this is same as f times t applied on g. So it is clear that t star equal to, because we should get t star, but we are getting the same t, therefore t star is t. So though t is self-adjoint, but we can immediately see that t has no eigenvalue, because if possible let t as eigenvalue. Let t as an eigenvalue. Then we can see that this will imply tf equal to lambda f for some non-zero f. Non-zero function f. But this will imply tf means t times ft. So this means t times f is same as lambda f. That is t minus lambda times f equal to 0. But this is not possible, right? T minus lambda times f equal to 0. This is not possible. This is only possible because t minus lambda is non-zero function. Therefore, this f must be 0. Okay. So from here we are getting a contradiction. Therefore, though it is self-adjoint, but it has no eigenvalue. Hence, it has no eigenvector. Okay, A is false. Now, what about B? For for finite dimensional inner product space V, the normal operator T will have an orthonormal basis of V as eigenvectors of V.
Sir, this is false. In
B.
case of real, it will fail, sir.
Okay. So if something is not given, we will always consider the field as complex. Okay. So
Why,
for
sir?
yes,
Why?
it is
Sir, anyone can, sir.
yes.
Can the reader feel as a real, then it
Yes,
is not.
whatever you are saying is true. That if the this option actually depends on the field, given field. So in general, the rules is that if the field is not given, not considered, we will assume the field as complex C. Okay.
Sir, where the rules are written, sir.
This is not rule anywhere it is written. We always assume those kind of fact.
Okay,
For
sir.
example, like, we always consider, so every polynomial has a root.
Yes, sir.
So
In,
this
sir,
is
in case of complex.
yes, this is only true when the given field the field is considered as complex. Otherwise, this is not true.
Sir, when it is, sir, chosen correct, sir, then
Yes.
then it is
So
obvious that the field is complex. But if
yes,
the statement is asking that every polynomial has a field, if we treat it like a question, then it is not always true.
yes, you may say, you may matlab, you can say like that, but I will consider it as true statement because I'll consider the given field is. So let me add something. So the vector space, add this fact, the vector space is considered over C. Okay, this is added to this question. Then B will be true, right? This is why the normal operator. This is the property of normal operator.
Spectral theorem, sir. Why?
Yes, by spectral theorem or whatever you say, that is, it is always diagonalizable, and the interesting fact is that those P inverse, those P are actually unitary. So for B, any normal operator T is always diagonalizable. So if we considered A as some matrix representation, then there exists P, and so we have P inverse AP. This is diagonal, and the interesting thing is that those P, those are actually unitary matrix. Unitary matrix. So this is actually, this says any normal operator T is unitarily diagonalizable. Those are unitary operator, therefore unitary means those are actually, those columns are actually orthonormal, right? Therefore this is true. And what about question number C? Here the linear operator is considered T. Now W be a subspace of V, which is T invariant. Then the orthogonal complement of W is T star invariant. Is it true? So let us see. So given W is T invariant.
Sir, I think this should be true.
Yes, this is true. Let us check. So T invariant means T applied on W is contained in W. Okay. Now let us take some element W dash from W part. Okay. Then we are trying to prove that T star W dash, this belongs to W part. We'll try to prove this fact. So T star W dash, this belongs to W part. That means if we take inner product with any W belongs to W, this should be 0, right? For all W belongs to W, this should be 0. Because we are trying to prove T star W dash, this also belongs to W part. So we know this is same as TW comma W dash. But TW, this is an element from W. Because W is T invariant. Therefore this belongs to W and this belongs to W part by consideration. So the inner product must be 0. So this is true. Therefore we are getting that T star W dash belongs to W part. Okay. In other words, T star applied on W part, this will contain in W because those the element W dash is considered from W part. So T star applied on W part contain in W. So C is true that W dash is T invariant. T star W part the orthogonal complement, that is T star invariant. Now the question number T, it says that every Hermitian matrix is orthogonally equivalent to diagonal matrix. Is it true?
Yes, sir.
So there is a slight problem here because we already know that will be, so given T is self-adjoint, is it? T is Hermitian and self-adjoint same.
Yes, sir.
T is Hermitian. So we know that Hermitian, therefore, in particular, T is T is unit normal operator, and I have just stated that fact that T is unitarily diagonalizable. That means if we take any matrix representation A, P inverse AP is diagonal. But the the issue is P is unitary. Unitary means all the columns form an orthonormal basis. But the problem is P may not be real. That is the issue actually. So though P is unitary, P may not be.
You are talking about field.
No, orthogonal. What is the meaning of orthogonal matrix?
Orthogonal if a matrix is, sir, unitary, sir.
No,
Then it,
orthogonal.
then it is orthogonal, sir.
There is two definition. One matrix is called
Okay, sir.
unitary.
If normal, then orthogonal, sir.
Yes. So unitary means, so for a matrix, unitary matrix means P star P
Is
and
equal to identity, PP
yes.
star.
But orthogonal, that
Only
means
commute.
yes. P transpose P is same as PP transpose is identity. So that's the issue. So that is actually, that notion is actually very confusing because we say those columns are orthogonal, but we don't say this is orthogonal matrix. We call it unitary matrix because we also take conjugation. P star P. The problem is that in complex inner product, that is defined as Z W bar, not just simply taking product. That is, for any A comma B or U comma V to pair, the product is defined as U transpose V, U transpose V bar, or sorry, maybe U bar transpose V. So conjugation also arises. That's the problem. So
So
unitary,
if field is, sir, is real, then this is true.
yes. For real, this is true. For real, unitary and orthogonal, those are equivalent thing. But for imaginary,
Yes,
because
sir.
P may contain some imaginary parts. That's the issue. So
But
if
sir, if we take your, sir, previous statement, sir, as true, that you said that if field is not mentioned, then we will consider as complex.
yes, complex. That's why in complex case, unitary does not imply orthogonal, right?
Yes, sir.
That's the issue. So this is not true. So let me give an counter example. So if you choose A to be 0 I minus I comma 0, again standard basis, that is I am considering some function, some linear operator from C2 on C2, and standard basis is considered. So if A is chosen as this matrix, you can see that eigenvalues are
Plus
plus
minus.
minus 1. But
I, sir.
yes, so if we now check the eigenvector with respect to plus 1, the eigenvector
Sir, eigenvalues are plus minus I, sir, na?
No, it is plus minus 1. Why this is true? Because, okay, let me check. Maybe I.
Yes, sir, plus minus 1.
Okay. Because you can see that trace
The
is.
dry square is usually, sir, minus 1, so
Yeah.
yes.
So from trace and determinant, you can easily.
Yes, sir.
Okay. So with respect to the eigenvector plus 1, eigenvalue plus 1, we get the eigenvector this. Let me check one eigenvector. Let us compute one eigenvector. So what is a minus lambda I? That is a minus 1 I. This is same as minus 1 minus 1.
Minus 1, I minus I.
Yes. So from where here it is clear that so if we row reduce, then second, now this is linear. The second row will be automatically linear dependent. Therefore, only first row will survive, and second row becomes 0 0. If we just subtract, multiplying with I and subtract. So from here it is clear that the solution space of this matrix is same as we need to take plus I here and 1 here, right? If you just multiply with plus I, uh, minus 1 times plus I means minus I, and I times plus 1 means 1 I. So plus minus I vanishes. So this is eigenvector, and with respect to minus 1, the eigenvector will be again similar calculation. It eigenvector will be minus I comma 1. Therefore, what is P? P will be same as I comma 1 first eigenvector and then put the second eigenvector minus I comma 1. But we are trying to get unitary matrix. Therefore, we need to we need to divide those things by some norm. That is, for example, norm of that element. It is same as 1 by root 2. So we take this eigenvector. Therefore, P is same as this, and P inverse AP will give the diagonal this plus 1 and minus 1, right? So from here it is clear that P is not orthogonal. So D is again wrong. Okay, so let us solve question number 3. Here the matrix A is given as ABCA. ABCA. So we need to find a condition such that this A represent a normal matrix, a necessary sufficient condition of this. So what is the condition for normality? So normal,
So commute A theta A star is equal to A star. Right?
yes. So this is A, and what about A star? A star means it is
A
conjugate.
conjugate B conjugate column wise.
Yes. So we need to take conjugation of B and switch the place. And similarly conjugation of C and switch the
B
place.
conjugate.
So this is if and only if this, and this is if and only if. So compare each entry. Okay.
Modulus A square, sir.
Yes. First entry will be mod of A square. So let us write all those entries.
Plus
Mod A
plus
square,
modulus B
mod B
square.
square. Yes.
Is equal to B. Modulus C A square plus modulus C square.
Yes. So this is true if and only if mod a square plus mod b square is same as mod a square plus mod c square. Right? Those two entries are same. And we can note that other entries are automatically same. This is AC bar, AC bar, A bar B, A bar B. So other entries are automatically same. Only this need to be whole. That is this equality. And this is if and only if. So A get cancelled. So this is same as mod B. This is same as mod C. And this is if and only if B equal to. Then what will be the answer? Modulus of both thing are same.
E to the power I theta.
E to the power I theta. Such that where theta belongs to real.
Yes, sir.
So this is not true because, for example, if you choose theta equal to I, then you can see that
It will become real, sir, and it will be I 1 by E. Modulus will be 1 by E times.
B will become C to the power I times I, that is C by e to the power minus 1, that is C by E. So this is not possible because then mod B and mod C, this will imply mod B not equal to mod C. Because mod of E is not 1, is something greater than 2. So D is certainly C is not 2. So only B is 2. Because if and only if. So those conditions will imply those B equal to minus C, B equal to C, that will imply A is normal, but reverse is not true. Because we can choose something, for example, C to the power I pi by 4. For example, if we choose this, then B is not same as C, B is not same as minus C. So only B is true. So let us see question number 4. Here you can see P is again complex C2. And it is equipped with standard inner product alpha beta 2 element. Now we need to check which are sesqui linear form or simply which are formed. So to check something is formed, we need to check those properties.
A is not such.
Yes.
A
So
is not a form.
A is not a form. Why?
It is not linear.
Yes. So again, we know that inner product satisfy those the or any t of the transformation of 0 will be same as 0. So any linear operator or linear transformation sends 0 to 0. And similarly, this is also true. That is, if any component is 0, then f of 0 comma beta, that is 0. Or f of alpha comma 0, those are actually 0. This is the proof is very simple, and it is actually similar to that earlier. F0 beta can be written as f0 comma 0 beta, 0 plus 0, and this by linearity on the first component. This is true. Now f0 beta 0 beta cancel, therefore f0 beta is same as 0, because f0 beta cannot be 2 times f0 beta. It will be only true if f0 beta is 0. So the proof is same. Therefore, it is clear that A is not formed. In option A is not a form, because f of 0 comma 0, this is not, this is actually 1, which is non-zero. So A is not a form. Now what about B? Can we say B is form?
But there is square term. I think it will not.
Yes, absolutely. If we have earlier seen that if we write explicit formula, what where is the yes here
Transpose it.
yes it will look like, so with respect to any basis it will look like this, right? If we expand any form it will look like xi yj bar times some scalar, so this is denoted as aji, some scalar times xi yj bar. So we can see that xi times xi, those type of square thing will not appear, right? So from here it is clear. Otherwise we can also check linearity property. For example, if we write, so take for example, let us check with f2 comma 0. Okay, f of 2 comma 0, this is actually same as 2 means sorry, it is not 2 comma 0. Let us say take f of 1 0 and then 0 1. Okay, so the first thing will become x1 minus y1, so that is same as 1 square plus x2 times y, that is 0 times 1, so 0, this is 1. But now if we take f of 2 comma 0 comma 0 1, so if this is v, this is actually 2 times v. So if we take this thing, now this is same as x1 minus y1 bar, which is 2 minus 0 bar, which is 4, right? 2 square plus n 0. So this is 4. No, this is not same as 2 times the previous one. So it does not satisfy the linearity property. Linearity in first component. So B is also not true. So B is false. Now what about the C? So it seems like some square appears, but if we see carefully, so if we just write explicitly, this is same as 4x1 y1 bar, right? So again this is a form, because we can check the properties. F of alpha, we have earlier already seen that any form can be written as sum of aij into those xi yj,
Yes, sir.
xj yi, and it is from here it is clear that a11 is 1 and other entries are 0. So this is clearly a form, and we can also check those linear and other properties. For example, f of alpha plus alpha dash, maybe,
So this is clear, sir.
yes, you can check those property. So check linearity. This is a form. So C is a form. Now what about D?
This is also true.
X1 y2 bar minus x2 y1 bar. Is it a form?
Sir, it seems to be.
Yes, this is also formed because it is also can be written as sum of aji or whatever you say aij xj yi bar. Okay, so the matrix representation of this form, what will be the matrix representation? Matrix of the form,
Sir, 0, 1,
yes,
row wise, sir. 0, 1, minus 1, 0.
yes. So there is no 1 1 term, there is no 1 1 or 2 2 terms, so those diagonal will be 0. And uh, now what about the 1/2th component? So
With
one,
respect to standard basis, na, sir?
yes, I am taking the standard basis. 1 2 means
1, 2 means
component.
even E2.
Yes, this component, right? So
Image of, sir, even E2.
yes. Also, you can compare from here, right? You can. Uh, so this will be 2. This will be 1. That is, so it is opposite to whatever we choose.
So I think, sir, we have to check the image of 1001, na, sir? To
You
get,
can
sir,
take using those
even.
kind of thing, image of E1 and E2. Otherwise, you can also check from this comparison, which is much easier because you can
Yes,
see that A11 from this comparison, comparing we are getting.
sir, but this will work only in case of standard basis, sir.
Yes, that will work only for the standard basis. Otherwise, this will fail. So A11, you can see that A11 there is no coefficient of x1 y1 bar. So A11 is 0, A22 is 0, and now what is A12? A12 is the coefficient of, this is coefficient of x2 y1, coefficient of x2 y1 bar. But x2 y1 bar means my coefficient is -1. Similarly A21. So we are getting -1 here and +1 here. Okay, so D is also a form. You can also check with those. You can check linearity. It is very easy. Linearity and conjugate linearity. So on the first component it will be linear. On the second component it will be conjugate linear. So CD both are formed. Now question number 5 here. The form is given. The explicit formula is written here. Now we need to find matrix representation of this form. So let us find the matrix representation by the way you said. So again, standard basis is under consideration. So E1 means it is 1 0, E2 means 0 1. So we'll take f of, so what is, in general let us denote it by some alpha 1 alpha. Okay. So what is f of alpha 1 comma alpha 1? What will be that?
Sir, 1, 1.
Yes. So alpha 1 comma alpha 1 means only x1 will be 1 and rest of the thing, so it is 1 0, right? So
Oh,
x,
sorry, alpha 1, yes, sir, yes.
yes,
Correct.
x1 and x2 are 1, so only
2.
this term will survive. So this element will be 2. Now f of alpha 1 comma alpha.
So this is 1.
Yes. So alpha 2 means this is 1 0 0 1. So only x1 y2 this product will survive. So x1 y2 means it is 1. Similarly, f of alpha 2 alpha 1. Alpha 2 means this is 0 1, this is 1 0. So only y1 x2 this product will survive. So where is y1 x2 this term? So this is minus 1, and f of alpha 2 means y1 y2 term. Coefficient of y1 y2 is minus 1. So those will survive. Therefore, the matrix representation, this is given by f of, so if the matrix is A, then Aij is same as f of alpha j comma alpha. So first one will be alpha 1 1, that is A1 1. A1 1 is this 2. Now what is 1 2? 1 2 means alpha 2 alpha 1. So 1 2 means this thing. This is A1, right? So A1 2 is minus 1. Then A2 1, which is plus 1. A2 2 is minus 1. So this will be the answer.
Sir, I have seen in some books that the sir entities are defined in the same order, sir. Like sir, A12 is
Yes, it may depend, because if we follow this Hofmann-Kunze, it is means a form. This is actually written as y transpose, means it is written as y star x, where y is the coordinate of y, x is the coordinate of x. If we use this notation, then a should take this form. A will look like this kind of f of alpha j alpha. Otherwise, if you take no, this is actually needed. Otherwise, this will not work.
sir Aij is defined as sir f of alpha I alpha j, sir. In some books, sir.
Which aij
Yes, sir.
is defined as f of alpha I alpha j.
Yes, sir. The same order, sir.
If you define like that, then this may not hold, because if that is symmetric form, that will hold. There will be no issue.
Yes, sir.
But otherwise those two will be different. For example, here those will be different. Yes.
Okay, sir. This is true in case of bilinear form, sir. And
Yes, that
but
will
sir,
be called bilinear. If
every bilinear form is symmetric.
yes, if
Okay,
you
sir.
consider symmetric, then there will be no issue. Okay, and you can also from immediately you can also just check
Sir,
your.
all bilinear form need not be symmetric, no, sir.
Yes, here it is up to now. It is not symmetric. No symmetry is not considered. Okay, so let us see question number 6. Txy is given linear operator. We need to find sesqui linear form corresponding to this linear operator. So as we have earlier seen that sesqui linear form, any linear operator correspond to some sesqui linear form, and the formula will be like this: f of alpha beta, this is same as t alpha inner product beta. So again, standard inner product is considered. So we need to find, here alpha is x1 y1 in our question, and beta is x2 y. Now what is t alpha? T alpha is same as ax plus by comma cx plus dy. Means there will be x1 y1 x1 y1, because we are taking t of alpha. This is actually T alpha. Now what is beta? Beta is x to y. So x to y. Now we know that inner product is defined by what is T of alpha comma beta. This is defined as alpha beta bar transpose. That is this times this, row times columns, taking conjugation. Okay. So now if we just multiply, the first one will be a x1 plus b y1 times x bar plus c x1 plus dy y1 times y2 bar. So just expand, we are getting a x1 x2 bar plus b y1 x2 bar plus c x1 y2 bar plus d y1 y2 bar. So this is same as uh, option C, right? Option C or D. B y1 x2 bar. So this is, okay, option D is the correct answer. Now question number 7 here. Operator T is given. We need to find the resolution of the identity with respect to E1, E2, E3. Sorry, resolution of the identity operator, that is E1, E2, E3. We need to find that. So let us say something about normal operator. So some properties, those should be stated. So what is spectral theorem? Spectral theorem says that any normal operator
over field of complex number is unitarily diagonalizable.
yes. So any normal operator over C, over finite dimensional inner product space, finite dimensional inner product space over, this is on, over complex field C. This can be written as so for any normal operator, those corresponding to distinct eigenvalue. Suppose Ci I equal to 1 to k are distinct eigenvalue or characteristic value, then those eigenvector eigenspace. So also let Wi is the eigenspace corresponding to Ci. Then it is clear that those Wi and Wj, those are orthogonal to each other. Then Wi and Wj, those are perpendicular. Their inner product are 0 when I not equal to 0. And another interesting thing is that if we take Ei, this as projection of V on those Wi, then this T can be written as those C1 E1 plus C2 E2 up to Ck Ik. So any normal operator can be written as linear combination of some orthogonal projection. Okay. Those are orthogonal projection on.
So what are C1, C2, Ck?
Those are eigenvalues, distinct
Yes.
eigenvalues.
Okay, sir.
And interesting thing is that those Ei times Ej, those are 0. Means those are delta Ij. Means if I and j are distinct, those are their product is 0. and if I and j are same, the product is 1. Because ei square, what is the, we know already, we know that projection square is same as I. Okay, so those are actually orthogonal projection, therefore uh, sorry, not that, e square is same as e, so I am writing something wrong. Ei times ej, this is 0 for I not equal to 0. Because wi and wj are perpendicular, those spaces are perpendicular. Therefore, if you take
Yes.
projection on wi, then if you take projection on another wj, that projection will be 0. Okay, so this is the spectral theorem, and yes. So what is spectral resolution? So spectral resolution is defined as like this. So from here, it can be seen that identity operator I, this can be written as E1 up to Ek, because we already know any vector V, this can be written as, because W1 up to Wk, those are sum of this W1 up to Wk will be phi, whole phi. So whole phi can be written as W1 up to Wk, right? Therefore, any vector phi, this can be written as small w1 up to small wk, such that where wi belongs to wi, small wi, this vector belongs to capital W, the vector space. Therefore, we can see that, but what is w1? W1 belongs to the first space w1, right? So this is actually orthogonal projection E1 of W, E1 of V. Similarly, WK, this is orthogonal projection of V on W. Okay, and this is unique. That is, this representation is unique because those W1, W2, those are perpendicular to each other. So you may not have different representation. Those are unique representation. Okay. So from here it is clear identity applied on V is same as this. So identity can be written as E1 up to Ek. This is called resolution, spectral. Sorry, this is called resolution of identity with respect to the normal operator T. Okay, so this is called resolution. And another interesting thing is that, so you may ask how to find those this combination, right? How to find E1 up to Ek? Because that finding is not straightforward. First, we need to find those eigenvectors, and then we need to find eigenspace corresponding to all those eigenvectors. And after that, we need to again construct projections E1, E1 up to Ek, those orthogonal projections. So there are lots of steps, but the interesting thing that this process can be reduced. Okay, so let me say that important fact. So if T can be written as sum of Ci Ei, again Ci are eigenvectors, T is normal operator, normal, Ei are those projection, on those subspaces. Okay, characteristic spaces, orthogonal perpendicular characteristic spaces. So I equal to 1 to k. If t can be written as this, then for any polynomial, f is any polynomial, so let fx is same as sum of n x to the power n equal to 0 to r, any polynomial. If fx is like this, then ft can be written as, from here it is clear that just replace x by t. So this can be written as ci t to the power n, cn t to the power n, right? N equal to 0 to r. But the interesting fact is that if we expand, this is same as f applied on those ci. Sorry, this is n. I have just replaced this x by t. Okay. So if we just expand, this is same as f of ci ei, where I is same as 1 to k, distinct, corresponding to distinct eigenvalues. Those are distinct eigenvalues again, right? So this is the important fact. Ft, any polynomial ft can be written as f applied on those characteristic polynomials ci and take their sum. Is it okay? F applied on the whole t is same as f applied on ci and take the sum. That is, it behaves like linear thing.
Sir, how will we get the polynomial, sir?
Okay, from this step to this step.
No, sir. How will we get the polynomial, sir? We randomly take any polynomial.
Yes, for I am saying that for any polynomial, so this thing an t to the power n, this can be written as this.
Then, sir, this will not be unique, sir.
No, this is given a polynomial. So fx is a given polynomial. So suppose I give you a polynomial, so I expect you to write ft. I ask you to find what is the value of ft. So you can
So, sir, the resolution is not unique, sir.
yes.
The resolution is not unique.
No, resolution is done. It is already done, right? Here I have not used anything resolution.
But you are, sir, telling how to get the, sir, resolution, sir.
No, I am not telling. Yes, I am asking how to find those E1 or how to find those E1 up to EK.
Yes,
Those.
sir. Okay, sir. The step is clear, sir.
So the thing is that that may not be unique because we can exchange those places, right? But if you write those as some increasing order, so suppose C1 is the lowest thing and CK is the highest. So if we write it as increasing order, then that is unique. Because those W1 up to WK, those are unique spaces. Eigenspaces are unique, right? With respect to some eigenvalue, eigenspaces are unique. So the projection are also unique operator.
Yes, sir.
Okay. So T can be written as this kind of combination, and that combination is actually unique. If we assume those C1 is strictly less than C2 and that is C1 less than C2, those are distinct. So C1, if we consider this order, then this combination is actually unique. Okay, so we are trying to find those E1 up to AK. So I said that if ft is a given polynomial, then it has a yes. So then it can be written as f of ci applied on ei. So those are some scalar fci times ei. This sum. F applied on t is same as f, just apply f on those ei. This is not in general true, but here it is true. Okay, because of those property. This property ei times ej, this product is 0. Sorry, ei times ej equal to 0. Using this property, you can easily check this can be written. For example, let us check a small thing, not general case. For example, what is t square? So what is t square? So t square is same as sum of ci ei times sum of again cj ej. Let us write as cj ej. So t square is, if we multiply those two things, then there will be ci times cj and ei times ej. Now ei times ej will get cancelled if I not equal to j. So ij both varies from 1 to k. So if I not equal to j, those will get cancelled. Therefore, only square term will survive. So this will be c1 square, e1 square. Again, e1 square is same as e1. Then c2 square, e2 square. But e2 square is same as e2, like this. So this will be c1 square, e1. This is because of ei times ej equal to 0 whenever I not equal to 0. And another fact, ei square is same as ei, because those are projections. So this can be written as sum of ci square ei, and this is actually same as, you can see that applying square is same as just take square of those coefficients. In general, applying any polynomial is same as just apply the polynomial on the coefficient. Just take f of ci here. So that is what I have written. So that is very easy to check. In this is for only for 2 degree. Now you need to consider t to the power n and just add this combination. You will get this formula. This is very easy to check. Okay. So this is an interesting thing, and from here, if we take this polynomial, so suppose ejx, this polynomial is same as product of x minus ci times cj minus ci. So where I varies from 1 to k and I not equal to j. So you have earlier seen this polynomial. This is called Lagrange polynomial, is it? Okay. So maybe this is called a Lagrange polynomial or something. So from here, the property of this polynomial is that ej times ej applied on cj will be 1, and if ej applied on any other thing, ej applied on ci, this will be 0 for all I not equal to j. Is it clear? Because
Cj minus Ci will cancel out.
yes, if we apply cj minus ci, that will be cancelled. So the product is product of 1. So that's why ej applied on cj is 1. And now if you take ej applied on ci, then there is, if you only take the ith component, then ith component in the product, it will contain ci minus ci, which is 0. So the product will vanish. So this is an interesting property of this polynomial. Now the interesting thing is that by this fact, what is ej applied on t? What will be that?
EJ applied on T. T, sir.
It
So,
is,
sir, summation, product summation, sir, CIEI.
yes, Ci. We are not writing identity, but whenever some scalar is written, just take multiplication with identity. Cj minus Ci. So this is actually I. There on the lower thing, there is nothing on the denominator. So this is I not equal to j. And now it is clear that this is actually same as Ei, right? This is same as Ej.
Same as EJ.
Why this is true? Because what
Sir,
is,
if
yes?
we, sir, consider product, then this will, sir, come out CIEI summation.
So you have already seen this fact, right? Ft can be written as f applied on the coefficient times Ei. So Ejt. So if you apply Ejt, this is same as apply Ejt is same as apply Ej on the coefficient Ci. But what is Ej Ci? You can see from here, right? Only ith term will survive. Is it clear? Ej Ci is same as only ith term will survive. This is only 1 and all the other terms are 0. So 1 times Ei, this will survive. That's why, sorry, EJCI means when I is same as J, since I varies, so when I is same as J, it will survive. So only EJ will survive. That's why EJ is same as EJ applied on T. Is it clear?
Sir, EJ is, sir, linear, sir.
No, EJ is not linear. Yes, capital EI, those are linear. But EJ is any polynomial. This is just a polynomial. This small EJ. It is polynomial like this, x minus c1 up to x minus some ck. But x minus ci is not there.
Yes,
And
sir. Correct, sir.
okay, so this gives how to calculate EJ. This formula gives the process to calculate capital EJ. Just
Yes, sir.
apply this EJ on T. Otherwise, it is difficult. Though this is there will be lots of calculation, but it is relatively easier because
EJ.
now we don't need to calculate all those things. Projection, first
Yes.
find those base eigenvectors and then take projection. We can avoid
We
those.
need to calculate EJT.
Yes, only we need to calculate those products. EJ. Yeah. So back to this question number 7. So let me move it to somewhere else. Okay. So now we need to calculate those. It is 3-dimensional. That's why we need to calculate E1, E2, E3. It may not be 3. It can be less than 3 because there can be less number of eigen.
But it will depend on eigenvalues, no, sir?
Yeah. So there can be less number of thing also because it may happen that only E1 and E2 are there. So let us find this E1, E2, E3 in this case. So we need to find E1, E2, E3 such that I can be written as E1 plus E2 plus E3. So as we have seen, that E1, what is the formula for E1?
Sir, first we need to check T is sir normal.
Yes,
We
is
can
normal. It is not given, right? Okay. So what is T? T is same as. Let us write the matrix for T. That is matrix representation of T with respect to standard basis. So 4x minus y minus z, that is 4 minus 1 minus 1. Then minus 1 minus 1 4. And then minus 1 4 minus 1.
sir, we write it as sir in columns, na sir. Take transpose.
Oh, sorry. No. This is okay because if we apply 1 0 0, this will be 4. This is minus 1. This is minus 1. So 4 minus 1 minus 1. Then minus 1 plus 4. And then if we apply 0 0 1, this is minus 1 plus 4 minus 1.
So this is by chance symmetric, sir. That is why it is true. But you have
Yes.
written in sir row.
It is in general true, right? Because let me write
We
something.
when we sir check sir write it sir when we take sir coordinate vectors, na sir.
Yes. Whatever
Coordinate.
you are saying is correct, but I am saying a different thing. So suppose txy is same as ax plus by, comma cx plus dy. Then I am saying that t is simply ab cd. I am writing those first thing is here and second thing here for the standard basis. Otherwise, so why this is true? Because you can write just change from row to column. So t times xy, this is same as ax plus by, cx plus dy. So this is same as abcd times xy. Is it okay?
Yeah.
So this is always true. So you can either just apply t on e1, that will give the first column. T on e2, that will give the second column. T on e3, that will give you the third column. Or otherwise, you can directly observe those first thing. First will be in the first row, second one will be in the second row, third one will be in the third row. So you may choose anything. Okay, so this is the matrix representation since it is uh, symmetric, that is self-adjoint, therefore normal. So now we need to express identity. That is, we need to find the resolution of identity. So identity can need to be written as this. Where E1, E2, E3, those are actually projection corresponding to those eigenspace, perpendicular eigenspaces. Okay. So let me give the name A. This is A. Okay. So now uh, what is A minus? We need to find eigenvalues. So what is A minus lambda I?
Sir, please show the matrix, sir.
Yes.
Can you show the matrix, sir?
Yes.
Sir, I think one eigenvalue is sir 2, sir.
Okay, how can you say this?
Because sum of each column is 2.
Sum of each column is 2. Okay, nice. Yes.
And you can now take trace.
Yes, whatever you are saying is true actually. That is some, yes, your approach is correct, because sum of those three columns are 2. Therefore, if we take 1 1 1, that will give 2 times 1 1 1. Yes. Okay. So let me do in the earlier manner. 4 minus 1 minus lambda. This determinant. Now this is same as 4 minus lambda minus 1 minus 1, and then minus 1 minus lambda. This is minus 4, and then this is minus 4, and now we subtract, we do R3 minus R2. Okay, then this will become 0. This is 5 plus lambda, this is minus 5 minus lambda. And similarly, if we do C3 minus C2, third column minus second column, then minus 1 will get cancelled, so it will become 0. This is 5 plus lambda, and this is minus 10 minus 2 lambda. So now it is now easier, but again we can take 5 plus lambda common from the third column. So this is 5 plus lambda times 4 minus lambda minus 1 0 minus 1 minus 1 minus lambda 1 0 5 plus lambda 0 minus 2. But again this is same as again we can apply those operation so that one get cancelled, right? So yes. So this will becomes, everything is unchanged, 5 plus lambda, and this is 4 minus lambda minus 1 0. And now what we can do, we can subtract, we can just remove the third thing. So minus 1 minus lambda 1 0, there will be no, there is, it will change. So this is minus 2 3 minus lambda and 0. So we have done this operation, C3 plus 2C2. So now this is same as 5 plus lambda times 4 minus lambda times 3 minus lambda. So I am checking this thing actually, this determinant 4 minus lambda minus 1 minus 2 3 minus lambda, this determinant. Okay, so one eigenvalue is lambda is minus 5. From here it is clear that equating with 0, determinant a minus lambda equal to 0, that will give either lambda equal to minus 5 or this thing is 0, but this thing is 0, that will, if you expand, this is 4 minus lambda times 3 minus lambda minus 2 equal to 0, but this is same as lambda square minus 7 lambda plus 10 equal to 0, and this is same as lambda minus 5 times lambda minus 2. So either this equal to 0 or this equal to 0. So we are getting those three eigenvalues, minus 5, plus 5 and plus 2. So I'll write it in increasing order. So those are eigenvalues. So those eigenvalues, set of eigenvalues, those are actually called spectrum. So this is therefore spectrum is minus 5, 2 and plus 5. In finite dimensional case, this is called spectrum. And now we need to find capital U1. So let us recall that what is U1x? U1x
minus.
So this is C1, this is our C2, this is our C3. Those three eigenvalues. Yes. X minus
Ci
Ci. So there will be C2 and C3 term because I not equal to 1. And now we just replace
C1 minus C2, C1 minus C3.
yeah, C1 minus C2. So we need to calculate all those things. So that's the difficulty, because not difficulty but lots of calculation. So what is E1? E1 is same as E1 applied on T. But so I'm not finding U1, but I am finding that is matrix representation of this U1. Okay, so that is what is x minus. So this is our A. So I need to subtract C2 from this thing. So if we subtract C2, what is C2? C2 is same as 2. So this is 4 minus 2, minus 1 minus 2, minus 1 minus 2. And similarly, yes, and similarly, we need to subtract C3. C3 is plus 5. So we are getting minus 1 here and minus 6 here, minus 6 here. Similarly, all the other things are unchanged. This is minus 1 plus 2. And now what is C1 minus C2? C1 minus C2 is
Minus 7.
minus 7. Sorry, C2
Minus 10.
minus C2. This is actually wrong. I have done some mistake. Is it? Yes. C1 minus C2.
That is correct,
Minus
sir.
7. Yes, it is correct. Yeah, it is actually okay. So first one is minus 7 and second, sorry,
Minus 10, sir.
and then minus 10. Now if you just multiply, those are I have already calculated. So that is 1 by 70 times, yes, yes. So this is 1 by 70 times. Uh,
First term will be 0.
so that calculation is also not so difficult because it is symmetric. You only need to calculate the upper those terms, and other terms will automatically calculate. So this is 35, this is minus 35, this is also 35. Therefore, by symmetry, this will be minus 35.
Sir, if A is symmetric, then A minus lambda is also symmetric, sir.
Yes, because sum of two symmetric thing is symmetric, right?
Yes, sir.
Diagonal thing is always symmetric. So this is same as half times 0, 0, 0, 0, 0, 1 minus 1 minus 1, 1. So this is actually E1. So if we write, if we now apply E1 on XYZ, what will be that? Just take this combination, right? So that first first row is 0, so that will be 0. Second row is 0 plus y minus z by 2. Third row is 0 minus y plus z by 2. So that will be E1. Now if you do the same calculation, it is easy to see. That is, let me write the formula for E2. E2 will be E2, the representation of E2, that is same as E2T, this representation. So I am denoting the representation, matrix representation. So the matrix representation will be same as uh, by the same formula, x minus C2, instead of x minus C2 there will be so this is the matrix representation is considered, so this is considered as A, right? So this is A minus. Now what do we need to subtract?
A minus sir C1 I, A minus C3 I.
Yes.
C2 minus C1, C2 minus C3.
Yes. So if you calculate this, again this will look like 1/3 and everything is 1. Just calculate. Check this thing.
XYZ.
Yeah. So from here it is clear that E2 will look like, so first row is 1 1 1, therefore x plus y plus z, but there is 3. And all those are same. Okay. So what is E3? Again the same calculation. For E3 we need to use that formula, E3 of x. This is same as x minus C1 times x minus C2 by C3 minus C1 times C3 minus C2. So E3T, that is E3, is same as E3T. So from here, the matrix representation of E3, that will, if you can easily check that will be same as 4 minus 2 minus 2 minus 2 minus 2 1 1 1. So from here, again, what will be E3 applied on XYZ? So from first row it is 4x minus 2y minus 2z by 6. From second row minus 2x plus y plus z by 6. From third row minus 2x plus y plus z by 6. So that will be the matrix. And that will be the operator. So we have successfully found the operator E1, E2, E3. Right?
Sir,
Yes.
we can find sir E3 sir without using this formula, sir.
Yes, you are right. But you should find, because there can be some mistake. If you made some mistake, you you will not get.
Sir, there is also possibility, sir, by mistake, sir, mistaking in this formula, sir.
Yes, those can happen. But
Probability is same for both things.
if you directly subtract E1 E2 from identity, then you will automatically get E3. But the problem is you may make some mistake. Yes. So there will be less possibility if you calculate everything, because you can find that mistake. Otherwise, you may not find. So, which option is correct? A, B, C. Maybe this is actually D. So D is correct, right? First one was this, second one is this, and third one 4 minus 2 minus 2. Yes. So
Sir,
D.
these, sir, you have got sir minus y minus z minus y plus z, sir, enough in even.
Which thing?
Even sir, even there is a y minus z.
Yes. You are right. B is correct. B is correct. Y minus z by 2 and y plus minus y plus z by 2. Now everything matches. Okay. Yes. So B is correct. 7 point B. Okay. So let us solve the next question. Here it is. So this is continuation of the 7, question number 7. Here txyz is written as this, the same tree. We need to find the value of t square. We already know t square, right? What is t square? So we need to find spectral resolution of t square. So let us see the definition of spectral resolution of t. So t can be written as C1 E1 plus C2 E2 plus C3 E3. This is actually called spectral resolution of T, where Ci are distinct eigenvalue, and E1 are those previous projection occurred. So that this is called spectral resolution of T. So
T square is C1 square E1 plus C2 square E2 plus C3 square E3.
yeah, we have already seen that is same as just so. If you take any polynomial, apply that polynomial on the coefficient, right?
Take sir polynomial as a x square.
Yes, we'll take the polynomial x square. So apply x square on C1, that will give C1 square. So we are getting C1 square E1 plus C2 square E2 plus C3 square E3. Now what was C1 square? We have already found that
C1 square was
yes,
25.
minus 5 plus 2 plus 5.
5.
Those are C1, C2, C3 eigenvalues. So that will be first one will be 25 E1 plus 4 E2 plus 25 E3.
4E2.
E2, yes. So we have earlier seen the formula. So that is the correct formula, right? Y minus Z by 2. And so we have already found that E1, E2, E3. So this is E3 and this is same as this.
Sir, E1, E2, E3 will also depend on C1, C2, C3. Sir.
Yes, that is that will depend. That's why I have already said that we always write in increasing order. C1 less than C2 less than C3.
But sir, in previous case, sir, C1 was sir minus 5 to plus 5. But in our case, in this case, sir, we have sir 25, 4, 25.
Yes, 25.
They are sir, sir change, sir. Then
Uh,
how can we relate this to the previous question?
yes, whatever you are telling is correct. That's why we will always take that previous choice.
No, no,
That,
sir. I am saying that we have to calculate it again, na, sir.
no, no. So let me say
Okay, okay, sir. Got it, sir.
yes. For T, the order is already determined by T. Now, whatever any polynomial is given, any polynomial of T will choose the same order. Okay, but it will also not depend because from 25 that is already given. That's why you can already exchange those things.
Sir, but my question was, sir, that when we calculated E1, sir,
Yeah.
we use sir CI, sir.
For calculating E1, we have used all those things.
Yes, sir. But
Yes.
if in this case we calculate, sir, then we have to use sir C1 square, sir. C1 square, C2 square, C3 square. In case of sir C1, C2, C3 in place of. Then we have to calculate again, sir, E1, E2, E3, sir. How they are coming like this.
Yes. Whatever you are saying is true. Uh, in this, if you do in that way, then there will be a problem because now there are 225, right? There will be so if you directly calculate, then corresponding to T square, there will be only one eigenvalue. There will be two eigenvalue. One is
Sir, whatever the power of T we raise, the EI will be same as that of T.
yes, EI will be same. Eigenspace is same because from here you can easily check if TV is same as lambda v, then T to the power nv is same as lambda to the power nv. We have seen.
Yes, we same for yes.
Yes. But the problem is these two different lambda can merge.
Yes, sir.
That's the issue actually. So maybe so if you use this definition, spectral resolution. So let me check the definition actually. So that should be the correct definition. Spectral resolution, that is we write T as linear combination of all those projections, and those C1, C2, C3, those are in ascending order. So if we write in that way, then there should be only single 25. That is, so we have seen that D is correct. So those two will be merged, these two things.
Yes, sir. Because 25, 25 are same.
Same, yes, yes. So let me check the definition actually. Whatever you have raised, that question is genuine. Okay. Just a minute. Yes, so page number 344, there the definition of resolution is given. So resolution of identity. Sorry, this is not the definition. So where is the definition? No, no. Okay, I cannot find it now, but you can check the definition of resolution. Okay. So definition of resolution of the identity operator is already given, but I cannot find the resolution of the given operator T or any power of T to the power n. So you can look at the book actually. But the process is clear, right? How to find this kind of decomposition. So here the option D is correct actually. Okay.
Yes.
Main thing is that we want to decompose T as sum of projection. That is the main goal. So those are actually sum of projections. Projection on eigenspaces. Yes. Let us check question number 9. Now it is easy. Here, inner product is the standard inner product, and the linear operator on V, this is defined as Tg, it is multiplied with F, given continuous function or given polynomial. Now we need to find adjoint of this T. Okay, so we'll start with Tg and G2, Tg1 times G2, this inner product.
So T star always exists, sir.
Yes, for finite dimensional case, T star will exist, but here we are considering infinite dimensional, so we need to check. Okay, so Tg1, G2, this is same as, what is Tg1? This is 0 to 1. Sorry, Tg1 is F times G1. This is the definition. G2. And this inner product is defined by 0 to 1 if G1 times G2 bar dt. Now this inner product is same as, so we can exchange the place of F. So G1 times, so we can take double bar of F. So F bar G2 and bar D. We can write it as this, right? Right? Because F double bar is same as F. So there is no issue. Now this is same as G1 times F bar G2 inner product. So from here it is clear. Uh, so, but this is actually same as G1 times T star G. So comparing those two sides, we are getting T star G2. This is same as F bar times G. So T star is exist. T star exists, right?
Yes.
Now what about? So this is false. Now T star exists. Uh, is T star self-adjoint? So
T star self-adjoint means T is equal to T star, but here we see that there is conjugate.
yes. So T star G, we are getting T star G is same as F bar times G, but Tg is same as F times G. But in general, those two are not same. For example, take F to be same as just multiply with I. So I bar times G, that is minus C, and I times G is plus C. Those cannot be same. Those are two different functions. So clearly, therefore, T star is not T. So T is not self-adjoint. Self-adjoint. So this is false. Now what about unitary and what about the normality? Okay. So we need to find T star times T. So T star times Tg, that is same as T star applied on Tg is same as F times C. But T star is same as multiply with F bar. So this is F bar times Fg. That is norm F square times G. But we can write in another way. So F times F bar G. Right? But F times this is same as T applied on F bar G. But F bar G is same as T star applied on G. So this is true for all G. Therefore T star is same as T star. Hence T is normal. So this is true. T star and T commutes. Now what about another thing?
It is not unitary, sir.
Yes. So if we assume T star T is identity, then this should hold. But the problem is that this will imply, if we assume this will imply that T star T we have already computed. That means mod F squared G is same as G. So this may not be true. That actually means mod F is 1. May not be true. Take the constant function F equal to T. So again, therefore, this is not this is not unitary. B is false. Okay. There was another question: singular value SVDs, singular value decomposition. So we'll discuss later in the next week.
There is no week left today after this day.
Yes, that is true. It is the last class, but I have taken another extra class. So we'll again not in the next week. In this on this Sunday. Sunday we'll discuss.
Sunday, sir, in afternoon, sir.
Sunday that usual slot, that is 6 to 8.
Okay, sir.
Okay.
Sir, your video is paused.
Yes, I don't know what is happening, but my video is paused. Yes. Okay, so do you have any question?
Yes, sir.
Yeah, please go ahead.
Can I share the question, dear sir?
Can you just tell it briefly? Okay, let me stop the recording and you may share.